Welcome to lecture 28 of our system protection course. In the last lecture, that is lecture 27, we discussed about the static relay. In fact, we finished the static relay portion, and in the last lecture we discussed how the static relays can be in fact implemented using the discrete electronic components. So, for both cosine type and sine type phase comparators, we have seen how it can be implemented using different discrete components, discrete electronic components. And also we have seen also how an amplitude comparator can be implemented, because it is very easy to implement the amplitude comparator by simply using one op-amp, right? So, it is easy as compared to the phase comparators. So, therefore, the complexity lies in the phase comparators. So, therefore, in detail we discussed the cosine and sine phase comparators, how we can implement using the discrete electronic components. And then we talked about how one quadrilateral relay, quadrilateral distance relay can be implemented using different types of static comparators. And finally, we completed the static relay portion, and today we will see the numerical relay, which also is known as and in other terms we call it digital protection system, because when we feed the analog signal into an microprocessor for numerical processing, it needs to be converted to a digital signal before processing. So, therefore, we need the analog to digital conversion facility in the relay system. So, let us talk more about digital protection schemes, and then after finishing this portion of digital protection system, we will little bit discuss about the circuit breaker, and then your course will be completed. So, let us start with, so here we can see this is just an overview of evolution of an ammeter, how an ammeter is gradually evolved into an overcurrent relay, because we know the ammeter principle of ammeter, analog ammeters, just feeding the current here will feed the current, right, in the both the terminals are being fed by the current, right. So, in fact, ammeters we connect in series in any circuit to measure the current. So, when we feed the current, there is a coil which creates the deflection torque, and also there is a spring here, right. That spring will create the opposing torque, restraining torque, right. And in fact, this is the principle applied in the electromechanical overcurrent relay. So, therefore, it is said that because the principle is same, so therefore, the ammeter is evolved into an overcurrent relay. So, we can see here, if we can put two contacts of trip coil, right, trip contacts, then whenever there will be overcurrent because of the fault or because of some disturbance, then obviously this needle will move and it will touch these two trip contacts, right, and it will give the trip signal to the circuit breaker. So, this ammeter also can be used with some arrangement as a relay, overcurrent relay, but we know because of we want to reduce the weight of this needle, and therefore we use, and also in order to set the time setting, there are certain more arrangements have been made to just modify this arrangement of ammeter into an overcurrent relay. We call it aluminum disc overcurrent relay, right, where we have two settings generally. One is your time dial, as where we make the TMS setting, right, time multiplier setting. Then another is a PSM setting, clock setting multiplier, where we set the reference current, right, current, and here we give the time, right, time setting. So already we have discussed in detail all these things, and also we know that from the wattmeter the directional relay concept has been evolved. We know this very well, right? Because in the wattmeter we know that, if you have studied in your instrumentation course, I don't know, there are two coils. One is your current coil, right, and other is your pressure coil. So both our current coil is being fed by the current, and pressure coil is being fed by the voltage. If we will mark it as VPC and the current as ICC, and if we will plot the phasors, obviously when the current is in right direction, in forward direction, right, then we can say that it will trip. That means your needle will move and it will connect the trip contacts, right. So that means the wattmeter principle is also same, almost same as the directional overcurrent relay. When the current flows in opposite direction, the needle will move in opposite direction, right. So this is what, because that will develop the negative torque. So this is what the principle of wattmeter and the directional relay, they are almost similar, and therefore it is said that this directional principle of directional relay has been evolved from a wattmeter, principle of wattmeter, working principle of wattmeter, right. So already we have discussed these things, no need to discuss more about this, and let us move forward. What is in fact how the numerical relay came into picture, how it evolved. So in addition to the ability of quickly disconnect a faulty element of our system from the rest of the system using CTPT in conjunction with the relays and circuit breakers, there are many routine things which need to be attended. So not only we are worried about the faulty part, isolating the faulty part, so that is what it is mentioned. We are also need to attend many more things. For example, let us consider a 100 MVA transformer that is placed in a substation. So we need to do the following functions in addition to protection. In addition to protection, we need to do the following things, like display the status of the circuit breakers. This is very important on either side of the transformer on a control panel, and this is very important. And second is metering of energy, active and reactive power, peak demand and power quality, all these things we need to meter. Then annunciation, logging and flagging, these things are just to record the data in the transformer, what is happening. Then archival of data, right. Then keeping count of the number of circuit breaker tripping to facilitate CB maintenance, because CB, the circuit breakers maintained after so many operations, there are certain operations, after that it is maintained, okay, the maintenance is being carried out. Therefore it is very important to keep count of the number of circuit breaker operations or trippings, right. So keep a check on the health of the trip batteries. This is important by monitoring their voltage level. Monitor and display the tap changer position, always it is necessary, right. Then communication with the substation computers. This is also essential in order to send the data from different points, right. And such other functions except the communication, except the protection aspects, which are distinct from the protection per se, are called control and automation functions. So one is protection function, already we are talking about, and now these other functions are called control and automation functions. So much of the data used for the control and automation is common with that used for protection. So many data is there common in fact. So therefore we can very easily imbibe, or we can very easily combine these aspects, protection, automation and control, right. So further, the computational processing requirement of the control functions is very small as compared to the protection, and can easily be accommodated in relay hardware and software. So if we will compare the computational aspect of control and automation, it is much less as compared to the protection function. So therefore it can be easily accommodated in the same hardware and software. Thus, it was very natural to merge the control and automation functionality with the protection functionality, giving rise to what is known as numerical terminal. Okay. So, it is known as numerical terminal, sometimes it is also known as remote terminal unit, right, remote terminal unit, or in short we call it RTU, right. So, this is also known as numerical terminal, dedicated to the protection, control, automation and monitoring of a particular element of the power system. So, in a single unit all the functionality has been embedded, that is called the numerical terminal. So, the modern numerical relay has thus evolved from a torque balancing device to a programmable information processor. Now, it is evolved as a programmable information processor, we call it numerical relay, right. So, because there is a processor inside it which computes and then gives signal. So, we can implement an existing relaying concept using the numerical technique. However, the possibilities of developing a new numerical relay are almost endless and there is very little standardization. So, we can develop any kind of relay as per our requirement, but it should match with the functionality of the power system very well. So, therefore, there is endless kind of design we can make, but how it is possible, how we can, what is the process, how to develop this numerical relay concepts, right. Let us see it. So, we can see this is the flow diagram of development of a relay, numerical relay, right. So, first what we do is we state the relaying problem, okay. And then after that we mathematically model the relaying problem, then for that we write the algorithm. Then when we model mathematically the relaying problem, we run the simulation over some simulation package like MATLAB, Simulink or some other packages, EMTP packages, right. Then this run, then after simulation the data was tested with the simulated data, right, and then the algorithm whatever we write for the model, relaying problem model, it is being written in the high level language, that should be put in the machine language, that is called high level language, in order to burn into the processor, right. Then here it is test both the data from high level language and the simulation result, both are tested. If it is working okay, right, if it is working okay, then if it is yes, then generate the machine code for the target microprocessor or digital signal processor. If it is no, then again we need to modify the algorithm, then again we modify the program, and again we test with the simulated data. So, this simulated data is being compared with the high level language, which is tested with the simulated data, whether it is matching the result or not, right. If it is yes, then the machine code is generated for the target microprocessor or digital signal processor, then it is downloaded to the numerical relay, and then again it is tested with the test inputs, right. So, these test inputs were collected from the relay test bench, from the practical hardware setup, that is called relay test bench. So, from the relay test bench we get the analog voltage and current signal, and it is fed to the numerical relay to test it, right. So, then it is tested, and if it is working okay, if it is yes, then install in parallel with the existing relay, right. If it is no, then again we need to modify the algorithm, and then we have to write the program and change the program, again high level language program. If it is yes, then we have to install it in parallel with the existing relay, and we need to feed the real life inputs from CT and PT to the relay, and then this process is evaluated, the performance of this kind of relay is evaluated over 2-3 years, right. of a period of 2-3 years. Then after that it is ready for commercial launch. Okay. Then after that only, so it is a long process in fact to develop a numerical relay, right. For beginning to the commercial launch, it takes a lot of time, around maybe it takes 5 years from the basic level to the launch to the commercial relay, right. So this is how the numerical relays are developed, and it is being used in this practice is followed to develop the numerical relay. So next is the architecture of the modern digital relay. How, let us see what is the architecture. So this is in fact the architecture. We can say the architecture here, these are the top, this is the top level, right, top level, and this is the last down level, right, down level. So we can also do here top to down level approach, and like in this, first we need to develop the algorithm for control, automation and monitoring functions. Then we need to develop algorithm for implementation of relay characteristics or protection scheme. Then we need algorithm for extraction of information from raw samples. So we have raw samples like analog current and voltage signals. From there we need to extract the information, and then we need in order to extract this information we need analog to digital conversion, right. This is very important, and before the signal is being fed to ADC, analog to digital conversion, right, it must pass through a sampling and holding circuit. This is very important. And then your filtering, signal conditioning, it is very important. Anti-aliasing filtering is required for that in order to restrict the bandwidth of the signal to satisfy the Shannon principle, right, Shannon theorem. We will talk about in detail in the next class, right. So then obviously the analog signals are being collected from CT and PT. CT and PT feed the analog current and voltage signals, and then it is converted to digital signal, and then it is processed, right. So our main agenda here will be the third layer. This is the third layer, right. We will develop few algorithms. We will see few algorithms which are very important, which are emphasized on how we can extract information useful for relaying purposes. So we will emphasize more in this topic how we can extract information from raw samples. Also we will cover these aspects, ADC, then sampling and holding, filtering. Already CTP2 we have covered, right. All these things we convert up to this special emphasis on algorithm for extraction of information from raw samples. Okay. So rest we are not covering here. This is in fact the research, those are doing the research work, or you can say the postgraduate level, these things are covered. So this is a basic diagram for a numerical relay. So the basic the main building block is the microprocessor, right. We know this is a numerical relay, therefore a processor is very essential, whether it is a microprocessor or a digital signal processor, it is very essential, right. So microprocessor plays very important role. Then obviously we feed the analog signal from CT and PT to the anti-aliasing filter first, right. So anti-aliasing filter is a filter which in fact restricts the bandwidth of the signal in order to satisfy the Nyquist-Shannon theorem, right. So we will talk more about this in the next class. Then we have sample and hold circuits, and then it is fed to the multiplexer, then to the ADC, right. So obviously microprocessor gives signal to the multiplexer and sample hold circuit, right. So based on that these are controlled, and they give the signal they feed the signal to the ADC, right, analog to digital converter. Then from ADC the data is being fed to the microprocessor, right? And when it is feeding the data to the microprocessor, a signal is sent to the microprocessor indicating the end of ADC processing, right? Then your microprocessor as per the processing, after processing, finally it gives the trip signal, and the trip signal is sent to the power system, right? Okay. From power system, in fact, we collect the analog signal from CT and PT. CT and PT, they are in fact installed in the field from where we get the current and voltage signal, analog signal. So this is the basic building block of a numerical relay, how it operates in connection with the CTs and PTs, and how it feeds the trip signal to the power system. Okay, so let us see in detail. Let us first see introduction to digital signal processing, where this is very important. This is your analog world. This block diagram shows how we can interface between the analog world and the digital world, right? This is your digital world. Now the interfacing is your ADC, that is we call analog to digital converter, right? It in fact whatever the signal comes, it is converted to digital form and sent to the digital processor, and similarly the output in fact converted to analog signal using the DAC, right, digital to analog converter, and it is fed to the analog world, right. In fact, in case of power system, when we give the trip signal is in terms of 0 and 1, so it is digital signal. So therefore it is not very essential for protection purposes, it is not very essential to convert the digital signal from the numerical relay to analog signal. Therefore we do not require DAC in case of power system protection application. Right, here you can see very easily the functionalities, how it is being used in the relaying scheme, right. So here the analog signal is fed through the ADC to the DSP processor, right, to the DSP processor, and in fact this DSP processor gives the digital output, and it has, so this digital output can be fed directly to the required system. If not, if we need the analog signal, then we need one DAC, digital to analog converter, and we get analog output. So this is how it works. So here is your processor, we need ADC and DAC in order to get the final analog output from the DSP. Okay. So these are the basic building blocks. So now let us see in detail analog to digital converters, how it functions, and gradually we will see the rest of the part, right. So here we can see the analog to digital converter. This is a picture of n-bit bipolar ADC with input voltage range from minus Vm to plus Vm. That means if we have a sinusoidal signal, generally we collect the sinusoidal signal from field from CT and PT. So if you have a sinusoidal signal with peak of plus Vm and negative peak of minus Vm, so therefore it is called bipolar signal, right. So therefore we call it n-bit bipolar ADC with input voltage range from minus Vm to plus Vm, right. This is the range from minus Vm to plus Vm. So now we need to convert these kind of signals into the digital output with n-bit output, right. So ADC is we call it n-bit ADC, right. So therefore it is known as n-bit bipolar ADC with input voltage ranging from minus Vm to plus Vm. So our objective is to design this kind of ADC. So let us see how we can do this. So input and output of the n-bit bipolar ADC. Now I will see the quantization error when we send the analog signal to ADC. Before that, in the ADC itself we need to quantize the analog signal. So In fact, ADC is consisting of two blocks. One is called quantizer and other one is called encoder, right? So we'll talk more detail about the encoder in the next class. We'll consider here discussion for quantizer. So let us see the quantizer. The quantizer receives a sample of analog signal and converts it into its digital version, right? This is the function of quantizer, and then it is fed to the encoder and it gives a encoding signal in the output. So the input analog signal can take infinite number of values, right? If we'll quantize, it can take infinite number of values, while the output digital signal can take only 2 to the power n number of values, right? Because this is the n bit ADC, so therefore it can only take 2 to the power n number of values for an n bit ADC, right? So quantization leads to a definite loss of information, because if we see, obviously the quantization, if the number of bits will increase, then your quantization error decreases, right? So leading to an unavoidable error known as quantization error. So this is very important. Let us discuss more about the quantization error, how we can find this quantization error and how the information is being lost. We'll discuss, right? So this is a, let us consider a simple case of 3-bit ADC, right, where we are putting here analog input and we have output, 3 outputs, DO, D1, D2, they are the digital outputs from the ADC. Now if we'll see the analog input, we can just, we are considering here the analog input a V voltage V, right, and it is it's a ramp signal. Let us consider the ramp signal, right. So now if your voltage is 0 to V by 8, then it is giving 0 0 0. Then if it is V by 8 to 2 V by 8, it is 0 0 1. If it is 2 V by 8 to 3 V by 8, it is 0 1. How it is coming? In fact, let us see. So in fact, let us first we need to find the span, and if we will divide the total number of outputs, digital outputs in the span, then we will get the 1 bit, we call it 1 LSB, right. This is called 1 LSB, okay, 1 LSB, least significant bit, right. So now we can see here that if we will this is analog input, right, and this is your digital output. So your LSB is if your voltage is V, right, it is varying from 0 to V, it is a ramp signal, then obviously your number of our digital output is 2 to the power 3 for this, that is 8, right. So 8 number of digital output we have, then obviously your 1 LSB will be V by 8, right, that is obvious. So therefore we'll for each bit will increase one number in the digital output. So therefore from 0 to V by 8 your digital output will be 0 0 0, that is 0, and from V by 8 to 2V by 8 it is 1, 0 0 1, and from 2V by 8 to 3V by 8 it is 2 0 1 0. Similarly, these are decimal representations, right, decimal representations. Then from 3V by 8 to 4V by 8 it is 3, it is 0 1 1. From 4V by 8 to 5V by 8 it is 1 0 0, it is 4, right, it is 4. So similarly for 5V by 8 to 6V by 8 it is 5, 6V by 8 to 7V by 8 it is 6, from 7V by 8 to 8V by 8 it is 7, 1 1 1, right. So these are the digital outputs for variation of the different variation of the voltage. Now let us say how to, so all the voltages in the range of 0 to V by 8 are assigned the same code 0 0 0. Similarly, all the voltages in the range of V by 8 to 2V by 8 are assigned the same code 0, 0, 1 and so on. Thus the resolution of the ADC is V by 8, that is called 1 LSB, that is the resolution. So it is equal to 1 LSB, right. This is called resolution of ADC. So as the input voltage changes from 0 to slightly more than V by 8 volt, the code changes from 000 to 001, right. Okay. So thus the LSB corresponds to a change of V by 8 volts. The quantum of V by 8 volts is therefore called 1 LSB, and the resolution of the ADC is said to be 1 LSB, that is equal to V by 8 volts. So let us indicate the total excursion in the input voltage that the ADC can handle by V span, right. This is the total excursion if in the signal, and where V span can be written as V in maximum minus V in minimum, that is the total excursion. We represent this using the symbol V span, and that is equal to V in maximum minus V in minimum. So magnitude of 1 LSB for an n bit bipolar ADC with an input span of V span is given by this. So 1 LSB will be for a bipolar signal, it will be V span by 2 to the power n, that is equal to Vm minus Vm. This is for a sinusoidal signal. Now it will become 2 Vm by 2 to the power n. So this will give us the resolution of ADC, resolution of ADC, analog to digital converter, that is called 1 LSB, right, and here it is equal to 2 Vm by 2 to the power n, right, 2 Vm by 2 to the power n. Okay, so if we apply ramp to the input of the ADC, the output of the ADC will be quantized digital output. So let us see how it will look like. If we feed this to a DAC, it will generate a staircase type waveform, obviously, right. So we define the quantization error of the ADC as this. So quantization error I can define as output of the ADC that is seen through DAC. When the output of the ADC is fed in the DAC, it will obviously, if it is a ramp signal, it will give a staircase wave, right. So that means it is mentioned that output of the ADC as seen through the DAC minus analog input, that is ideal analog input which we are feeding, right. So that will give us the quantization error. Now we are considering we are considering a ramp signal, right. We can see here this is your signal, ramp signal, and now if we will apply the quantization mechanism, obviously from 0 to V by 8 it will remain 0, 0, 0, 0, and as soon as it little bit it is increasing from V by 8 more than V by 8, then it will suddenly increase to 0, 0, 1, then it will remain same at 0, 0, 1 till 2 V by 8, then just at the 2 V by 8 it will go to 1, 0, 1, 0, 1, 0, then it will remain at 0, 1, 0 till 3 V by 8, then again it will jump to 0, 1, 1, then like this it will go on, and it will give a staircase waveform, right. Okay. So in fact this is the output of the DAC when your ADC output is fed to a DAC, right. So this is this is your ideal transfer characteristic. This is your actual transfer characteristic. Therefore this is called actual transfer characteristic. That is the actual output seen by the DAC when the ADC output is fed, and this is your ideal transfer characteristic, right. Okay. So this is your staircase form, right. Now if we will find the quantization error, so quantization error says that this signal, that is the output of ADC seen through the DAC, this staircase wave minus this ideal transfer characteristic or ideal signal, right, actual analog input, that will give us the quantization error. So if we will find quantization for this case, for this ramp signal, then obviously we can see that the sawtooth waveform will get, right. This is your x axis. Now if we will see the output of DAC, it is 0 here, right. Now it will gradually increase, gradually it is increase means it is a negative sign here, there is a negative sign, right. So therefore it will become negative. So gradually it will increase in the negative direction till V by 8, right. Then suddenly at V by 8 it will become 0 0 1, that means it is achieving the point at the ideal transfer characteristic, this point. So at this point the difference will be 0, right. So again it will increase, as it will increase, again the waveform will decrease in the negative direction, right. It will increase in the negative direction till 2V by 8. So at 2V by 8 again it will become 0 here, right. So therefore similarly at 3V by 8 again it will become 0. It will therefore it will give a sawtooth wave, right. So and your x-axis is below this. Okay. So now the question is, in this, if we will consider this kind of case, then obviously your quantization error is more, if as compared to when, if it is in fact, if your input axis can be made like this at this point in the middle of the sawtooth wave. If we can somehow shift this sawtooth wave to the input axis, that means your input axis, your axis, x-axis will be in the middle of the quantization error waveform, that is sawtooth waveform, then obviously your quantization error will be less. So in order to make the x-axis in the middle of this sawtooth waveform, we need to have to shift this actual transfer characteristic little off, so that your ideal transfer characteristic pass through in the middle of the this staircase waveform, right, whatever we are seeing here. So in order to make that, we need to consider the half-LSB concept. So let us see it. So note that even an ideal ADC having no other imperfections cannot escape from quantization error, right, very difficult. So we can only make the quantization error smaller and smaller by increasing the number of bits in the ADC, but we can never completely eliminate it. We cannot eliminate it, but we can somehow, if we can just by increasing the number of bits, the quantization error can be decreased, right, more and more. So the error in the output of the ADC can be considered as noise signal. Obviously it will be considered as a noise signal attributable to the quantization phenomena. Hence it is customary to quantify the error due to quantization in terms of the signal to noise ratio. So generally the noise is computed in terms of SNR, right, we call it SNR, signal to noise ratio. So using the concept of signal to noise ratio, we can just quantify the error due to quantization, and it is obviously the ratio of signal voltage to the noise voltage, so usually expressed in the decibels, right. So the actual transfer curve of the ADC always hovers on the lower side of the ideal transfer curve. Statistically it will be more appropriate if the actual transfer curve symmetrically encompasses the ideal transfer curve. That means your ideal transfer characteristic passes through the middle of that actual transfer curve, then obviously it is more appropriate, and it in fact reduces the quantization error. So this can be easily achieved by adding a half-LSB offset to all the analog level at which the code makes transition. So just making an offset of half-LSB, this results in the error curve also being symmetric about the x-axis. So as I explained, the error curve also becomes symmetric about x-axis. So how it will happen, let us see. You can see here, just by introducing half-LSB V by 16, that means when the transition is occurring from 0 0 0 to 0 0 1, that should happen at V by 16, that is half-LSB, right, half-LSB. Then similarly it will happen again at 3 V by 16, again it will happen at 5 V by 16, it will again happen at 7V by 16 like this. Then we can see that the ideal transfer characteristic, obviously the transition is happening, transition period is obviously 1 LSB. So, but only we are creating an offset of half LSB, just shifting half LSB towards the left side, right. Now you will get the staircase waveform which is symmetrical along the ideal transfer characteristic, right. Okay. So, that is what is very essential. Now if you will see your quantization error, it will also become symmetrical about your x axis, right. Okay, this is your x axis. Now it will become symmetrical. In the lower side it is up to minus v by 16, and in upper half it will become plus v by 16. So, here upper is half LSB and the lower is minus half LSB. Obviously the total error will be, total span will be 1 LSB, right. Okay. Magnitude, total magnitude of the error will be 1 LSB, right. Now we need to find the error voltage. So, if we will find the expression for this curve, right, for this signal, this sawtooth wave symmetrically placed around the x axis, if we will derive the expression, obviously it will become minus VH LSB by T by 2 T, right. So, this minus VH LSB is nothing but this minus V by 16, right. So, that is called half LSB. So, half LSB voltage, right. So, in order to generalize the expression, we have written minus VH LSB by T by 2 T, and so it is obviously VH LSB will be equal to half LSB. So, therefore, your half into LSB, we know LSB is 2 Vm for a sinusoidal signal, it is 2 Vm by 2 to the power n for an n bit for an n bit converter, right. So, now it will become Vm by 2 to the power n. Okay. So, now we know V noise, if we will find the RMS value of V noise, this is the V noise signal. So, now if we will find the RMS value, if we will put the formula for RMS value, it will be 1 by T integration minus T by T2 to T by 2 V square dt. Now, the expression of V is here, this is your expression of V. Now, substituting here in case of V, we will get this. So, your V noise will become this just by substituting this and again integrating it. So, only T is the variable here. So, it will become T square and it will become TQ by 3. Now, taking out VH LSB, sorry, this is your LSB, right, VH LSB by T by 2 and this is also LSB, and so your final expression will become twice of VH LSB by root over 12, right. So, now your V noise RMS will become this. So, that is twice of Vm because VH LSB is nothing but Vm by 2 to the power n, right. Just by substituting V by 2 to the power n here, we will get this expression. Now, it will become Vm by 2 to the power n minus 1 square root 12, right. So, we found the V noise RMS and V signal RMS. We know V signal RMS is Vm by root 2 and V noise RMS is this, V noise RMS is this. Just by substituting, we will find the SNR, that is called signal to noise ratio. This is your signal RMS and this is your noise RMS. So, we will get the ratio of signal to noise. Then again we will convert it into decibel, we will see it in the next class, and also we will see various types of ADC, then your Shannon theorem, all these things we will cover in the next class, next lecture. So, thank you very much for your kind attention, and we will continue in the lecture 29 this digital protection system. Thank you very much.